For a volatile, a mixture of solute and solvent, where the components are volatile, that means the solvent is volatile and the solute is volatile. This is common for a liquid with a liquid. Mixing a liquid with a liquid. Liquids tend to be volatile to some degree. When you mix a liquid with a liquid, we're going to have two things that are evaporating into the gas phase. Of course, the total pressure is going to be the pressure of both components, the partial pressure of both components. So for an ideal solution, ideal mixture, we're going to add the mole fraction times the initial vapor pressure. So Raoult's law for a single volatile component, we're going to add that up for both components. So we're going to add up Raoult's prediction for each of the volatile components in the mixture. So the total pressure will be the solvent plus the solute, mole fraction times the pure vapor pressure for both of them. So this again is an ideal description. Works for some combinations, works for other combinations in limited ranges. So on the graph here, Raoult's law for a single component. So on the graph here we're doing heptane with hexane. So the bottom axis is mole fraction of heptane. So as heptane increases, its presence in the gas phase increases also. So when there's no mole fraction, zero mole fraction of heptane, there's zero vapor pressure for heptane. When we have pure heptane, the vapor pressure is equal to that of pure heptane. The ideal law has a straight line connecting the 2 points. For hexane, if we start off with a mole fraction of 1 of hexane, we have the vapor pressure of pure hexane. We go down to 0 mole fraction and 0 partial pressure when we only have heptane. So the ideal description is a straight line between the pure vapor pressure and 0. As we add these two lines together, what we end up with is the line that connects the two pure vapor pressures. So these are the descriptions from the Raoult's law for ideal solutions. So for heptane we see it increase from 0 to its pure vapor pressure. For hexane we see it decrease from its pure vapor pressure down to 0. And for the total of those two vapor pressures added together, the total pressure, it forms a straight line from the pure hexane down to the pure heptane. So this is the ideal description of two solutions. It works for certain combinations, but not for all. For all combinations, it should work in a limited range near the endpoints. So that would be heptane diluted in hexane and hexane diluted in heptane. For non-ideal solutions, we can have some dramatic variations. So let's look at the diluted areas first. So this is an example of carbon disulfide with acetone. It's a non-ideal mixture. We see that the total is not at all a straight line between the two pure vapor pressures. It's quite above a straight line above the two pure vapor pressures. We could use Raoult's law very close to a diluted solution, but you see this one is moving in an opposite angle greater than 90 degrees away from what Raoult's law predicts. So it only works for an extremely tiny mixture, and it's not even would not even pick the right direction from the pure. Raoult's law for the individual components is a better approximation. So for carbon disulfide with a small amount of acetone in it, they start off moving in the same sign, and for a short area they are close to each other. But then as the concentration increases, the gap between the predicted and the actual is getting wider. So within this small range, the Raoult's law is a reasonable approximation. For a small amount of carbon disulfide in acetone, though, the range that actually is a reasonable approximation is rather small. So it changes more drastically. For acetone with a small amount, those are the good ones, yeah. So the ideal approximation for Raoult's law works best on near the pure vapor pressure. So up in this area here, we see that the approximation between the predicted ideal line, straight line, and the real curve up through a sizable mole fraction is very close. The combination for pure carbon disulfide with a small amount of acetone in it starts to deviate more, but it looks like at least 0.1, within 0.1, 0.15 is a reasonable approximation. Okay, so on the left side of this slide, we have several combinations for interactions between solute and solvent. So we're going to have, we're looking at the interaction between the solute and solvent compared to, relative to, the solvent-solvent interactions and the solute interactions. Because to mix them together, we have to break solvent and solute intermolecular forces before we can create the solvent-solute intermolecular forces. So if these forces that are created between the solute and the solvent are similar or the same as solute interactions and solvent interactions, if they're all the same, then there's going to be no heat presented or exchanged. The heat level of the reactants are not changing. So the reaction is neither exothermic nor endothermic. So it's a non-heat reaction. So since it is not creating any heat or removing any heat, there's not going to be any change of temperature inside a mixing solution. This is an ideal situation. So this is the situation described by Raoult's law. But if we have a combination of solute and solvent that are very stable, they interact strongly, so they're going to be at a lower energy, than the solute and solvent interactions. So it has given up energy, so it's an exothermic reaction. So it has a negative enthalpy because it's going to end up at a lower energy, more stable energy. So this is releasing energy from these bonds. So we're adding energy to the solution, so we're going to have an increase in temperature. This attraction between the solute and solvent being so strong holds the mixture together. So less of it goes up into the vapor phase. So we end up with a decrease in pressure or a negative deviation from Raoult's law. If our solute-solvent interactions is weak, it's smaller than our original solute-solute interactions and solvent-solvent interactions. So if it's weak, that means it takes in more energy. It's not low energy anymore. It's higher energy. So this has taken in energy, which makes it endothermic. And it has a positive enthalpy. So it has taken in energy. It has more enthalpy present in it. So it gets that energy that it stores into these intermolecular forces from the temperature of the solution. It takes energy away, so the temperature drops. Everything starts to move slower with the energy stored in the attractive force. So with a weak attractive force between the solute and solvent, both solute and solvent tend to come out of solution more readily into the gas phase. So we have an increase in pressure of both components of the solution. So we have a positive change deviation from Raoult's law. We have a high pressure compared to Raoult's law. So we're going to have a high pressure when we have a weak attraction between the two components. We're going to have a low pressure, a negative deviation, when we have an attractive force between the two components. So if we add a non-volatile component to a solution, the vapor pressure will decrease. If the vapor pressure decreases, it cannot boil at that pressure. To boil, it needs the same or more partial pressure compared to the pressure that is on top of it. So if we reduce the pressure of a solution by adding a solid to it, a non-volatile solute, it cannot boil. So to boil, it needs to increase temperature. We need to increase temperature to increase the partial pressure until it equals the atmospheric pressure. So by adding a solid, a non-volatile solute to a solution, we have to raise the temperature to a higher point before it can boil, before it can pop a bubble of itself into existence, even though there is atmospheric pressure on top of it. So the partial pressure has to equal or exceed the atmospheric pressure before a bubble can form. So a solution requires a higher temperature to raise the vapor pressure up, since the vapor pressure is lowered by creating the solution. So we can describe this relationship, the shifting of temperature to the concentration with this relationship here, using the molality of the solute. So the concentration in terms of moles of solute per kilograms of solvent. So the molality. The molality is directly proportional to the increase of temperature. So as we increase molality, there's a direct relationship with the increase in temperature. On the Kelvin scale, the absolute temperature. And this is related to the molality concentration of all solute particles. So we have to include the Van 't Hoff factor when we have an ionic compound that creates more particles than the moles of compound. Then we have our relationship factor between the increased temperature and the concentration, Im. And this is our boiling point elevation constant. This will be unique for each solvent, so each liquid will have its own constant. So that's, as a colligative property, this does not require us to know the identity of the solute. We need to know the identity of the solvent, Kb, but not of the solute.